Welcome to IT Pro TV. I'm your host, Don.
Coming at you live from San Francisco, California.
You're watching IT Pro TV.
Hello, and thank you for choosing IT Pro TV, empowering the world through engaging learning. I'm your host, Zach Memis, as we continue on with CompTIA Net Plus, and this is classless IPv4 addressing. Interesting, huh? And Wes Bryant is here to tell us all about that. Wes, good to see you, sir.
Hey, Zach, thanks for having me back. That's right. You know, we have been moving through things like IP addressing and IP structure, and we've really been talking about IPv4 the whole time. But now we're going to get into kind of breaking the rules, right? In other episodes, we talked about the classes. We kind of identified those classes. And in this episode, we're going to look at some of the concepts behind how we kind of break the rules and we go with classless IP addressing, all coming up here in this episode.
So, Wes, why would we need classless IPv4 addressing?
Well, you know, they came up with a classical system at the time that basically the internet, or back in the days of the ARPANET, you know, when it first started out, they came up with a classical system, and it had a set of clearly defined walls, if you will. The problem is with the classical system, the system was very wasteful, and it's just because they really didn't know at the time that they came up with that system that there was going to be an exponential growth of, you know, devices, nodes, if you will, computers that would be out there, you know, on this thing that would eventually become the internet. We go through the dot-com boom, and what they noticed is that we were having, you know, just with that exponential increase, we were also having an exponential, well, depletion of the available addresses that we had within this 32-bit space.
That's exactly right. You know, back in the day, the old days, we used to think that an IP address was assigned to a house or like a unit or an enterprise. But not the case. It's per unit.
It usually is. You know, it's per host. Any host, right? Any node that wants to actually communicate across the internet in those days would have to have an IP address, right? Well, as they started to see that, hey, we were going to eventually run out of the available addresses, they said, hey, we've got to put some stopgaps in place to kind of stall, if you will, not to really eliminate it, because it was still going to happen, but can we put some kind of governor on it, right? Can we push the clutch in, and can we kind of ghost for a while, if you will, and try to stall the inevitable depletion, right? In other episodes, we come up, or we told you a little bit about that, you know, that RFC 1918, which is the Internet Engineering Task Force's request for comments for implementing private IP address ranges, right? Private IP address ranges were set aside because they said, you know what, this is going to help a lot of people. If you don't need to connect out to the internet, then what we'll do is we'll reserve in each of those classes. And in fact, let me kind of show you here. If you remember our classes that we were talking about in other episodes, and if not, go back and watch those episodes.
Yeah, please do.
Remember, we have our classes, and then there's only so many addresses within class A, B, and C. And then they put the private range in there, and they said, okay, we're going to make the private range here, and we're going to set these aside. And they don't have to be unique across the internet, but there is a stipulation. You can't route traffic across the internet with these, but you can use these internally on your own networks, behind your routers, right, and not communicate with the internet. Now, they also put into play, you know, some technologies like network address translation, right? And that allows us to take an internal private IP address and kind of do some packet mangling and replace a single public IP address, still using multiple internal private IP addresses. So that also helped to kind of stall the depletion of that classful system. Well, they kind of figured out that, you know, we got to go a little bit farther than that. We can't just reserve a private range. We've got to make it to where there's less waste. And let me show you what I mean here. You know, if we go back to the classical system, let's say that this is all we had was the classical system. And let's say that you got an IP, you got a network within this range, right? And let's go ahead, and I'll tell you what, I'll just kind of bump this font up here a little bit and make this a little bit bolder. And let's say, I don't know, you've got the 3.0.0.0 network, right? Well, you would have this subnet mask right away, right? 255.0.0.0. And remember, in other episodes, we said that those 255s represent 1 bits in the binary, and above that, where your IP sits, that means that that block or that octet is a part of the network range. Well, you can see that with a default or classful subnet mask of 255.0.0.0 applied to this IP address means means that we're going to have 3 octets that are reserved all for our nodes, right? Well, 3 octets is 24 bits, and if you do to the 2 to the power of 24, you come up with just under 17 million potential nodes.
Well, that's a few.
That's right, right? Well, here's the thing. What if you only needed 10 million, right? Well, you couldn't get one of these Class B ranges, right? Because a Class B range reserves 2 octets. You remember the zeros are our node bits. Reserves 2 octets for the host, which means it's 65,534 hosts you can get on a network, right? So if I needed 10 million, I would have to go into that A range, and I'd have to lease from an internet service provider. I'd have to get one of those Class A ranges. But the problem is, what happens to the other 6,777,214 node or addresses? Well, you can't lease those out to anybody else. So if you were a company that was big enough that happened to need 10 million addresses, you just wasted 6 million, because we can't just lease these over to anybody else, right? So that was a problem. Or what if you were a company that maybe you needed, I don't know, 3,000 addresses, all right? Well, you had a couple of things that you could do. You could get one Class B network, right? And that would give you the potential to have 65,533 nodes, but the problem is you only needed 3,000. What do you do with the other 62,000 addresses?
Give it to my Aunt Gert.
You can't give them, right? You can't gift them, right? It's not like the fruitcake. You can't re-gift it, right? And I know you like fruitcake, so I'm picking on Zach, right?
I like it. I'm sorry.
You can't re-gift it, right? And so those just become unused addresses. So what they were noticing is with this classful system, well, what would you do if you needed 3,000 addresses? Well, if I get a Class B, I'm wasting about around 62,000 addresses or so. In a Class C, well, in order to get that 3,000, remember that a Class C only has a single octet, the zeros reserved for the host bits, right? So at 8 bits, that only gives you 254 potential nodes, and we'll talk about why that number is 4 at the end of there. Well, 254 nodes. If I needed 3,000, that means I would have to get, what, 6 of those networks? I'd have to lease 6 of those networks to try to achieve my goal of having 3,000 nodes. So that isn't necessarily a lot of waste. It's more wasted money for the employer or for the person, you know, that needs to lease those IP addresses from the internet service provider. So again, you had a rapid depletion of C networks because of the fact that, yeah, they're smaller, but you'd have to get more of them. So there really was no in between. So the classful system, again, it implemented a lot of waste, right? Or it brought about a lot of waste because of those addresses. They said, well, what if, right? What if we break the rules? What if we say, you know what? We're going to come up with a system called Classless, and we're going to allow you to manipulate this subnet mask any way you need it in order to create the networks that you need with the amount of nodes you need and with the least amount of waste, all right? Or at least to reduce the waste.
Right.
And that's where the classful system comes up. And there are some components within a classful system that you're going to have to be aware of. So when we talk about classless system, I want to start with a default subnet mask and kind of recap where we were when we were talking about things like decimal to binary conversion. If you remember, we said decimal to binary conversion. If you're not familiar with that show, definitely go back and watch it, because we're just basically using the exact same information that we were using before. But if you remember, I told you that the default subnet masks, right, that would be a single octet of 255 or 1 bits, right? So we have the network portion of your address would be any octet that's above those ones. Notice that in the Class B default subnet mask, we would end up having, well, what would it be? It would be 2 octets of 1 bits would be reserved for our network portion, and half of those, the other 16 bits, if you will, would be reserved for the node portion. And then last but not least, we have the Class B default subnet mask, which would be a set of 24 1 bits, right, on that side, right, 255.255.255.0, with only a single octet reserved for the node portion. So I want you to understand, you know, when we start talking about this, I want you to keep in mind that however many host bits we have, the more host bits we increase, the more host we have available, or host addresses we have available on that network. Well, with these fixed links, right, these fixed walls, There was no manipulation. If you had a 255.0.0.0 subnet mask on your Class A address, that means fixed. You would have all of these 24 bits reserved for hosts, and there was no way to manipulate it. And again, if we only needed 10 million, we needed a million. That would leave 15 million or more that would be completely wasted, right? How would you get up to that million any other way? Well, it would just be economically infeasible for the company because they'd have to get multiple, and I wouldn't even begin to do the math right there to, adding up 65,000 until you get up to a million, right? That's just not feasible. So again, it was a lot of waste. So when we start talking about the classless system, all right, I want to go back again. I want you guys to keep in mind that remember that when we talk about anywhere these 255s are, just keep that in mind that, hey, those are part of your network bits, right? Those are your network bits, and that's why I'm kind of keeping the same color coordination that we were going along with, right? So, and that's going to come into play because that's going to make it easier for some of the other things that we have to talk about in the classful system, or the classless system, excuse me. So notice that 255.0.0.0 is essentially one octet of 255s, right, in that first octet, and then your last three octets, the second, the third, and the fourth are all zeros, right? We've got 255.255.0.0. Again, that is the first octet of ones, the second octet of ones, and then the last, if you will, the last two octets, the third and the fourth, are all zeros, right? Well, and then the last one being 255 here, and if we look at 255, or I'm sorry, Class C subnet mask, if we look at 255.255.255, you can now see that we've got what? One octet, two, three, all the way up to the third octet of ones. The fourth octet is what is remaining for the host, right? So these were the fixed walls, right? These barriers that we have up here, and there was really no way to manipulate them before we went to a classless system. Well, in order to go to a classless system, what they said is, you know what? We're going to go ahead and we're going to let you apply any subnet mask pretty much that you want to IP addresses. We're going to let you manipulate the bits. We're going to break down these walls, and you can manipulate those bits to basically get less waste, to reduce the amount of waste that you have within those networks, and also to divide up the networks a little bit more to the way that you need them in order to accomplish whatever your network design might be. All right. So that's where we got to start talking about classless ranges, all right? And what we mean by that is we can start to add or take away bits, if you will, from the host side. If we take away bits from the host side, what are we doing? Well, I want you to think about up here, right? Just think about our subnet masks in general. If I go from having 3 octets of zeros, which is 16,777,214 possibilities.
Good.
Then what I do is if I go and I reduce that down to 16 of those zeros, right, what that does is it exponentially decreases the amount of nodes that I have, because now I only have 16 bits for the nodes. That's 65,534 possibilities. Right? If we decrease it even more, which is what the classful system would do, all the way down to 8 bits, well, now I only have 8 bits for my host, and that's 254 potential nodes that we can have on a network, right? Well, you might need to tailor it a little bit more. You might have to shrink it down, and maybe you want to add a couple of networks, which we call subnetting, and we'll look at here in a second, or you want to reduce the network even more, so maybe you only have 50 computers. Maybe I have a Class C network to start out with, and what I want to do is I don't want to just have these 8 bits and have all of these computers on one giant 254 node network. Maybe I only want 50 on one network. Why would I want 50 on one network? Well, it's not only about waste, it's also about broadcast domains. Remember, routers don't pass broadcast across their interfaces. So if I want to reduce the amount of broadcast, if you will, reduce or divide broadcast domains up, then what I can do is I can do what's known as subnetting. So subnetting isn't only done for an elimination of the waste of your IP addresses, it's also you can do this to divide up broadcast domains likewise. So let's go ahead and talk about these classless ranges, all right? You will see that our subnet mask still has to follow the same rules, all right? What are those rules? All right, from left to right, they have to be contiguous 1 bits. There has to be a dividing line between the 1 bits and the 0 bits, and there can't be zeros interdispersed in between the ones. That's why there's really only 8 numbers, and let me just count these, make sure I got this right. 1, 2, 3, 4, 5, 6, 7, 8 numbers that really can follow that concept of allowing your subnet mask to be contiguous ones. And these are those numbers, right? And if we look, I want you to think about it, right? If I was to say, you know what, I think up here, 255.255.255.0, I think I want to add another 1 bit in this subnet mask, all right? If I do that, let's say we just turn that on, and now that bit, if you will, is going to be no longer part of the hosts, but what that's actually going to be now is we're going to make that part of the network, all right? Well, how do I do that? I have to turn that from a 0 into a 1, and now it becomes part of my network bits, right? If I change my subnet masks, those 0s to 1s, 1 bits now denote the network, right? Well, what that does is that gives me an extra bit for the network, and we'll figure out how that works out possibilities-wise, but it reduces the amount of bits that I have for my nodes, right? So now I only have 7 bits for my nodes, all right? And if I have 7 bits for my nodes, then I go from 8 bits being 254 possibilities, I'm reducing it to 126 possibilities. All right, now we'll see exactly how this works, but you understand that if I apply a subnet mask, I also have to figure out what the decimal value of this binary number is, right? We still need to know because our subnet masks are denoted in decimal notation, right? Dotted decimal notation. So what is this number, right? Is it still contiguous 1 bits? Well, if you can look from the left to the right, I still have a contiguous 1s, right? All the way up to this 4th octet now. Remember, we're in the 4th octet here, but we've added a 1 bit. We basically what they call borrowing bits. You're saying, all right, I know that I've got a Class C subnet mask, and what I need to do is I need to shorten the, basically shorten the amount or reduce the amount of host bits, and when I do, what I'm doing is I'm increasing network bits in order to do that. Now that does a couple of things. If I increase a network bit, that also adds an additional network to your, or however many networks, we'll get into exactly how many, that's going to increase the amount of networks you have, but it's going to reduce the amount of nodes you have. And that's what we do when in order to have less waste. We reduce the amount of host bits that we have, and we do that with a classless system. Now, you might see that, I want you to know the bits. That's going to come into play here in a second, but notice that if I have 1 bit, we'll just focus on that last octet or a single octet at this point, right? We'll just stay in the Class C range because when you're first learning, it makes it a little bit easier, right? So we'll stay in that Class C range. And notice that in that last octet, Zach, I turned on 1 bit. I call it turning it on because if it's off, it's 0. Remember, if we think about binary and electrical impulses, the presence of electricity is a binary 1. The absence of electricity is a binary 0, right? Yes. So that's why I say turning it on. You might hear that, or borrowing a bit. Now, once I've borrowed that bit, I now have to figure out what this 8-bit decimal value is, right? Just like we were doing when we were doing decimal to binary conversion. Well, we also showed them, if you remember, how to do binary to decimal conversion, right? A lot of fun doing it. And then what that means is that I just use the same chart, and anywhere I see the 1s, I add up those place values. So I can see that 128 is still a single 1, and if I put it on the end of this octet here, it completes those contiguous 1s. So it's what's known as a valid subnet mask. All right. Now, in order to denote this in the decimal, I'm going to change that last octet. Now, instead of being a 0, because we've turned that 1 bit on, it's now a 128. So this is a subnet mask of 255.255.255.128. Well, I also want you to know that what would happen if we did that up here. So again, let's go to the default subnet mask of 255.255.0.0, and we say, hey, we don't want to follow the classes either. We want to kind of break all the rules. Well, I can do the same thing as long as the rule applies the same. Contiguous 1 bits. Notice that I got the first octet, second octet, that's 16 1 bits. They're contiguous. There's no breaks, no zeros interdispersed there. But if I turn around and I take this bit here and I turn it on, right, and I make it a 1, well, guess what? I still have those contiguous 1 bits. Nothing's changed. Notice I still got that octet right there. All 1s. Second octet, all 1s. Now in the third octet, I said, you know what? We're going to borrow some of those host bits. And what we're going to do is we'll take 1 bit and we'll turn it on. Well, guess what? We're still dealing in that third octet with an 8, oops, sorry guys and gals, we're still dealing with an 8-bit range, right? That 8-bit range, well, guess what? It's going to be the same value. But where we put the 128 is important here. I can't put the 128 out here because if I put the 128 out here, right, turn that on, now what we have is we have a problem, right? What's the problem here? Remember the valid subnet mask that we talked about. A valid subnet mask cannot have zeros and then the ones start up again. It's got to be contiguous 1 bits from the left to the right. So that is not a valid subnet mask. And that's something I wanted to kind of lead you into when we talk about the classful system, is understanding that concept. I can borrow the bits where I need, right? There's no longer these dividing lines, if you will, but the subnet mask still has to follow that same process of being contiguous ones. So the question would be, is if on the exam, if I see something like 255.255.128, well, is that a valid subnet mask? And you can see it is, right? We got 255, all ones, 255, all ones again, so we still got contiguous ones, but then in that third octet, I turn the first bit on.
Right.
So that's a 128, right? So that's 255.255.128.0. And you kind of have to understand that that's what's going on now today. What we can do is we can kind of vary that length of that subnet mask to suit our needs. Now, it's important to understand that concept, right? And it's also important to understand these valid subnet mask ranges. And it's also important to understand on the exam why something, if we go back up here to that 255, right? Why something like 128.255, or I'm sorry, 255.255, and let me take this back to classful. 255.255.0.0.128, why that wouldn't be a valid subnet mask. Why? Why wouldn't it be a valid subnet mask? Because, well, if I look at that and we go back to our binary, right? Remember, now we've got essentially a 0 in this third octet, right? So that means all zeros in the binary in that octet, and then our 128 was on the end, right? Well, I can't do that, right? And the reason I can't do that is because now I have zeros here, and then I got ones starting back up. It cannot be, subnet masks cannot be that way. You always have to follow that rule, right? They have to be contiguous ones from the left to the right, right? No matter how many we have, they have to be contiguous ones from the left to the right. So that is important to keep that in mind. And that's why you'll see that there are only really 8 ranges that follow this rule, right? Or 8 decimal values that you'll ever see in subnet masks that follow that rule. Let's start with one that you commonly have already seen throughout what Zach and I have been going through, with these IP structure episodes, right? Notice 255. Well, it follows the rule because the whole entire octet's ones. But I want you to also understand that this is not a valid subnet mask if I do something like this, if I do 255.255.0.255. Well, why is that not a valid subnet mask? Well, let's take it to the binary, right? What that would do is that would mean that we still have our first 2 octets, right? 255.255, those are all ones, but then we have a .0, which is zeros, and then from here in that last octet, if we put the 255s, well, what's going on? Well, unfortunately, that's not going to work because that turns these into ones, and remember what we said. You cannot have zeros and then the ones pick up. Not a single one. They have to be contiguous 1 bits. And that's why these ranges are really, really important here. Let me see if I can change these back real quick. All right. Now, let's not stop there. Let me go ahead and fix our non-examples of subnet masks, and let's kind of do a couple more, and then we'll probably come back and finish this here in a bit. All right. So, what if I decided that I was going to do 192, right? Well, is 192? Does it follow our rules? I don't know. Let's go ahead and let's mark 192. And let's see what 192 is literally in the decimal to binary conversion. Well, if you look, 192 is a 1 in the 128. 128 plus 64 is 192, right? My remainder is now zeros. The rest are zeros behind it. So notice that I got, even in just this octet, I've got contiguous ones. I got 2 1 bits from the left to the right. Well, if I put that on the end of these 255s, well, my 255s are all 1 bits, right? And then you add that last octet, I added another bit. Well, what has that done? Has that followed the rule of our subnet mask of being contiguous 1 bits from the left to the right? And the answer is true, right? So that is a valid subnet mask range, so you have to be aware of it. Well, let's not go there. Let's not stop there. What if I said, okay, well, we're going to go to the next one. We're going to go to 224. Now, I kind of have these memorized, so just understand you'll start to see them more and more, and you'll have them memorized. But just understand the concept before you worry about memorization and shortcuts. Don't shortcut your knowledge and understanding of the subject. Understand the subject, then work on the shortcuts, because you can get to the answer faster. But getting to an answer faster is only going to help you if you understand the underlying concept, right? So let's try 224. Well, for now, I just want you to go down to our chart here, and if you have to, pause the video. Copy this chart down. Write it down on a piece of paper and study it, right? So 224, well, that's actually 3 1-bits. Notice in that octet, because we deal with an octet at a time, that's 3 1-bits from the left to the right. So if I turn this into a 224, we already know, not to sit here and beat this over and over and over across y'all's head out there, just understand that the 255s we already know are our ones, right? Yes. I'm just focusing on that last octet right now. They call that where the action's at. All right, so now I'm going to take this bit and I'm going to turn it on. I'm going to borrow it from the nodes or the hosts, right? And we're going to turn that into a 1. And that's actually 224. And I do this color-coded because it makes it easier to see. You can see the green bar. Now, do I have contiguous 1-bits here with a 224 at the end? And the answer is yes, I do, right? So you'll start to notice this pattern, right? Notice that I have 128, 192, 224, 240 is 4 1s from the left to the right. It's contiguous 1s. Notice that I have a 248. That's 5 1s, 252 is 6, 254 is 7, and then we know all 1s within those 8 bits is going to be 255. All right, you have to know this, right? Because they might ask you on the exam, and then when we start to get into more subnetting, if you will, and learning more about our classless addressing, it's going to be important, right? You have to know and be able to tell, well, is something like 255.255.248, right? And let me make sure I write that right. 248, is that a valid subnet mask, right? Does it follow the rules? Well, I can tell you it does right away, but just because I know, I want you to know, right? Well, 248 is 5 contiguous 1-bits from the left to the right. So what that would mean then is going away from the classful, away from the defaults, right? We get into classless, we do 255.255.248. Well, that means I'm going to have 1, 2, 3, 4, and I believe 5. 5 bits that are now part of my node. And they very well, like I said, they very well might ask you on the exam to be able to do this. And that's why we take the time, because this really sets the stage for what we're going to do when we talk about subnetting, right? So you can see here that, yes, if I kind of try to zoom out there we go. You can see that, yes, we still have contiguous 1-bits. And this little chart will help you if you can remember these valid subnet mask ranges. If they ask you on the exam, is this a valid subnet mask or not? If you know the decimal conversions, if you know the 8 valid subnet mask ranges, then you're going to be doing good. What I typically do is I looked at the chart and I counted 8 bits on my hand. And I would map them up to those 8 bits. And I just do this over and over and over. So what I could say, okay, 1-bit's 128, 192, 224, 240, 248, 252, 254, 255. I know 255 is 8 bits, and I don't have to look at the chart.
But can you say that backwards?
I cannot do that backwards, and thank you for putting me on the spot there. That's right. So this is just the start. We're going to get into more, but these are some of the basics. When we come back in the next one, we're going to look a little bit more at what is known as CIDR notation and as it relates to the subnet masks whose bits we're moving all over the place.
Fantastic job, Wes. Thanks so very much. Classless IPv4 addressing, and there'll be a part 2 of that, and make sure you watch all the parts. And make sure you see everything in the CompTIA Net Plus series that Wes has put together for you. While you're in the course library, guess what? There's hundreds of other videos. They're all designed to help you go further. And tell everybody you know about IT Pro TV. They'll be mighty glad you did. Thanks for watching. I'm Zach Memis.
And I'm Wes Bryant.
And we'll see you soon.
Thank you for watching IT Pro TV.